Hey, BC Calc video 2. So this is an interesting problem because you might have been kind of confused about what do I do with this theta equals 1. First, theta equals 1 means the angle is 1 radian. So this is an angle of 1 radian, about 57 degrees, you know. And so that's not part of what determines what the radius is. That's what determines the first value that we're going to plug in, and then we're going to rotate from there up to pi over 2, because once we get up to pi over 2, then r goes down to 0, and we're back down to the bottom again. So thus, it's the 1/2 r squared d theta, but it goes from 1 to pi over 2, and you rotate through that angle. Kind of tricky there, because the 1 is kind of an unusual one for us. All right, what next? I'm kind of frozen a little bit, so we'll bring it back. There we go. All right, no calculator one. You can see this is kind of a similar one. It says let R be the region that is bounded by the polar curves R equals theta. So that's this curve down here, R equals theta, and this one here is theta equals K. Okay, cool. That's a really bad arrow. I'm gonna just redo it because it didn't look like an arrow. Okay, so what is the area of R in terms of K? Because K is going to be a bound on it. All right, so it starts off with theta being 0 and R is 0, and then it rotates up to theta equals K. So it's, what is the area? So the area, just rereading it, equals the integral from 0 to K. You can pause it if you want to work it out for yourself, see if you can get it. And it's the 1/2 r squared, and r is just theta squared d theta. Okay, which is equal to theta cubed over 6, 1/2 and then the 1/3, evaluated from 0 to k. So I'm getting k cubed over 6. Piece of cake. And finally, for your response. Now this one's a little bit tricky because this one is a loop inside of the loop, right? So it's like, oh, okay, what's going on here? Okay, it's the polar curve defined by r equals theta cosine theta. Let's graph this on the calculator and see what it looks like, just to help us out, because this one looks a little weird. And this was a free response number 2, so this was definitely a calculator problem. Okay, I've graphed it and I tinker with it a little bit. I switched over to polar because I actually want to see what this curve looks like. And I set the window from 0 to 3 pi over 2. And so I can hit the graph, and there's the curve, and it looks like what I thought it would look like. But I want to trace it and see, okay, what happens when I move around this curve? So when I plug in 0 at the beginning, theta equals 0, then I get 0. Okay, and then okay, that little inside curve is what happens as it goes from 0 to pi over 2, because once you get up to pi over 2, then you'd be back down to 0 again. So as the angle goes from 0 to pi over 2, it makes that little loop. But now as we keep going, theta keeps growing, and this keeps being a number between -1 and 1, but theta keeps growing. So that's why this thing is now going to start going further out. Now the r is getting bigger and bigger and bigger because theta is getting bigger. Theta is like 2.617 now. And so it's getting really big. And this is what happens as it goes all the way to 3 pi over 2. At 3 pi over 2, I know, remember, I'm up here, but it's because my angle is down here and I'm getting a negative r value. Now you can turn the format to, if you do second format here, you can turn things to polar coordinates on your trace. And so now notice it shows the r, and it shows my r being negative. And then it comes back, and then when cosine gets to 3 pi over 2 again, it would get back to there. So it does the little loop from 0 to pi over 2, and then it does the big loop from pi over 2 to 3 pi over 2. And even though it's pointing down because r is negative. Got it. Okay, what the heck is it going to ask me about this thing? Find the area of the region enclosed by the inner loop of the curve. So that inner loop, so that's where I needed to investigate that thing. The inner loop is going to be integral 1/2, and it's from 0 to pi over 2. That's where that investigation came in. And it's just a function, so I can even write r of theta squared d theta. And then plug that in my calculator. I want to go kind of fast here. Okay, so for theta 0 is theta to 3 pi over 2. So anywhere on this curve, find the greatest distance from any point on the graph of r to the origin and justify your answer. The maximum, right? So in the beginning, on my endpoints, at the beginning I'm at 0 and at the end I'm at 0. But the distance would be like the absolute value of the r, so it would be the biggest positive r or the smallest negative r. And I can see that this curve is really far out, somewhere out here. And so there's a point here where you reach the greatest distance. And so that would be where the absolute value of this was as big as, I'm sorry, the absolute value of this is as big as possible. But they gave me the derivative. So think about what this means. So there's going to be a point way out here where I reach the maximal distance away from the origin, like the maximal r. And what that would mean is that dr d theta, that r of theta has a local maximum, which means that dr d theta must be at a critical number, and it must go from positive to negative. So, okay. So I got what I'm going to do. So what I'm going to do is I'm going to say dr d theta is equal to cosine theta minus theta sine theta. Cool. And I'm going to set that equal to 0, and I want to solve that. Now, to solve that, to be honest, the easiest way to do that, in my opinion, is to not to do it on the polar curve, but just go back to regular mode. That's easier for functions, for setting things equal to 0 and solving it, because then the graph is much clearer. So I want the derivative, and I want to set that equal to 0. What was that derivative again? It's cosine theta minus theta sine theta. Okay, cosine x minus x sine of x. Check my window. Yeah, I only want to go from 0 to 3 pi over 2 because I don't care about other stuff. And the y's are fine because I just want to know when is this thing equal to 0. Okay, so what's going on here? So it was positive in the beginning because the r is getting larger and larger at the beginning, and then you reach a critical number right here where it reaches a local maximum, and then it comes back down again. And then it comes back out, and because it's negative. That's okay. So okay, we can solve this. So theta equals, and there's one value right here, which I can calculate the 0 there. Calculate the 0. What I like to do with zeros is just plug in numbers. So I say, well, 0.5 is too small, and 1 is too big, and that's fine for guess. So 0.860. Now, you had a lot more room on the real test to do this. So this is, I did not give you full room here. I apologize. We good? Yeah, I think we're good. Something weird happened there. Let me try to erase that and see if I can. There we go. Theta is 0.86. Weird, freaky, 0. Okay, well, you know what I'm trying to write. Yeah, I've got a part of on my surface screen that's having trouble. So theta is 0.8. That looks terrible. 0.860. Still having trouble. Okay, I'm moving on with my life. And what would be the other 0 of that thing? Calculate the 0 at 1, 2, 3. 3 is too small, and 4 is too big, and that's fine. 3.425. So, or theta equals 3.425. Now, you could just plug those, so the greatest distance, so that's the value of r. So I could plug this number back into the original function to find out which one gave me the r that was the biggest in absolute value, because it's going to be a negative r, but because it's just a question of distance, then that would work out. So I would plug these in, like kind of like when you do a absolute maximum on an interval. I plug in the endpoints, I plug in the critical numbers, and see which one's the biggest, and for the greatest distance. And the only thing is, you just would have to absolute value it because of the negative thing. Wow. Okay. Now, last one. There's a point on the curve at which the slope of the line tangent to the curve is that. At this point, dy d theta equals 1/2. Find dx d theta at this point. So this is the slope. So that's dy dx is equal to 2 over 2 minus pi. Well, this should be pretty easy here because I don't need to actually take the derivative, I don't think, because dy dx is just going to be dy d theta over dx d theta. So I could cross multiply and stuff, and so I'd get dx d theta equals dy d theta, and then I'm multiplying that by the reciprocal over to the other side, so times 2 minus pi over 2. I multiplied both sides by dx d theta, so it popped up here. I multiplied both sides by 2 minus pi, so that pops up here. I divided both sides by 2, so that pops up over there. And I solve for dx d theta. And dy d theta is just 1/2, so I'm getting 2 minus pi over 4. Think so. Looks pretty good to me. So for a moment, I was thinking I was going to have to use the formula, the dy dx formula, but because they gave me all the values I needed, that wasn't really an issue. And you see that they weren't really trying to test you on taking derivatives. What was challenging about this problem was understanding the difference between dy dx, that's what this is, and understanding where that comes from, and then what dr d theta is. Remember, dr d theta is the rate that the distance from the origin is changing as theta changes. So it's the rate that the r is changing as theta changes. And so if you've got a big dr d theta, a big positive dr d theta, that means you're moving far away from the origin compared to how much theta is changing. So you're kind of shooting out from the origin. If dr d theta is 0, that's a moment when you kind of crest and you have possibly a local maximum and you start coming back towards the middle, or maybe it's an inflection point. It'd be kind of a weird one. You'd be stopping being a certain distance and then curving away and being farther away or something like that. Anyway, that's what the problem was really highlighting. It wasn't really about doing algebraic stuff. All right, so what do you need to know about the area of the curves? So the area of a curve, of a polar curve, is, just going back, is 1/2 r squared d theta from the first theta to the last theta. But what gets tricky about these problems is that you have to think them through in order to figure out, well, what thetas do I want? And always go back to that idea of plugging numbers in, and especially looking at when you go back to the origin. That's very helpful in these problems. On this one, I was just concerned that I might have a negative r at some point, so I might be integrating it the wrong way or something. I wanted to feel comfortable about it, and I wanted to show you how we could think through what this curve is. And so by plugging in 0 and pi and thinking it through, I could see, oh, it starts at 0 and then it goes to pi there, and there's no negative issues on this one. Almost done. Just recapping. This one was a little tricky because theta equals 1 was there, and that was like, oh, that was a bound. That wasn't a curve I was using to find the area of. A little different there. And same thing on this one, basically, except this one you actually could integrate because it was an easy function. And finally, this last one, I like this last one because then I had to graph it on my calculator just to understand what was going on, and what were the bounds on the inner loop. Plugging numbers in really helped me with that. And you could plug numbers in by hand, but I did it by graphing it on my calculator. Okay, that's my 15 minutes of fame. So Take care, and we'll have an assignment posted, and have a great weekend. Let me know if I can help.